is commonly seen in mechanical systems. For example, if you have taken vibrations, if this is a mass block, and say this is the spring, and if this is the dampers, and here if we have the force here, F of t. And for this one, later in modeling, we would do a little bit more detailed modeling process. But here, for this given example, the governing equations can be derived as the mx double dot plus c, this is c, x dot plus kx equal to f of t. Let me use it in the lowercase f. How about let me using r? Okay. And let me start change the symbols and y. So this is the degree of freedom y of t. And again, in the following lectures, we will have the sections to show you how to derive the governing equations. But here we start with here. And so for this example, assuming we have the initial conditions and both are equal to 0. Okay, and today we have handouts there. So we take the Laplace transform of the whole equations, then we can obtain is m as squared plus c as plus k. And here, let me skip over the detail, assuming you can do it. And this one basically equal to r of s. Okay. So in this way, you can see the output per our notes. The output can be described by the m as squared plus c as plus k and multiply with the input. Okay. So basically here we have the information we can describe by this. So for example, if this is our input, then in algebraic expressions we can express into this, and this is our m as squared plus c as plus k. Okay. So that means this reading, the reading is y equal to this block multiplied with this one. Okay, this is called the block diagram, and we're going to have a quick review in the following few slides. So this is a typical, the second order degree of freedom, the second order single degree of freedom systems. And sometimes the people like to do this equations, do this governing equations with a different but equivalent format. And what is the format? Basically here we simply divide everything by n. So that means we divide everything by n, so that will be equal to y double dot plus c over n, y dot plus k over n, y equal to r of b divided by n. Okay. And they come up with certain definitions. K over n simply is defined by omega n squared. Okay, omega n is called the natural frequencies. And then in this way, for this term, we simply to make it into this equal to zeta times omega n. Okay, so here we find zeta such that 2 zeta times omega n equal to c over n. So in this way, here you can calculate zeta is equal to how much, right? So basically, here you can calculate, for example, 2 zeta omega n equal to c over n. So basically, zeta equal to c over n times 1 divided by 2 omega n. Okay, you simply plug in omega n here. So basically, zeta is the function of c, m, and k. Okay, so zeta is called the damping ratio. Damping ratio. So here we introduce two terms, and that is the one. If you have not taken vibrations, I think you need to pick up the two terms here. Okay, And usually, in most of the mechanical systems, damping ratio is less than 1. Basically, there's 3 categories. Damping ratio greater than 1, damping ratio equal to 1, and damping ratio less than 1. Okay, this is called the overdamped system, quickly damped system, and underdamped system. And here I want to emphasize on this in the handouts. Today we have handouts on the tables, help yourself. Okay, so for this case, if we have the second order differential equations of the vibration system, and then if we have the underdamped system, so here is the the second order system. So that is the starting point of the handouts I give you today. Okay, so here we focus on this one. So for example, here let me do follow up the form provided by our textbook. Y double dot plus 2 zeta omega n y dot and plus omega n square y. And here, for example, here this we take it is omega n square, but actually the right hand side can be any terms. Okay, here we simply take out this one. Okay. And again, our goal is to find out what is YT, to calculate what is YT. And in numerically, we can make it, maybe we can make one example here, say y double dot plus say 2y dot plus 3y, okay, and equal to something. I make it up. I didn't prepare for this one. I make it up equal to 1. Okay, and so in particular, we consider the initial conditions are equal to 0. So we don't consider the influence of the initial conditions here. So here y equal to y0 equal to 0 and y dot 0 equal to 0. Okay. So given this case, I believe you should be able to do it because this morning when I checked out the Blackboard, and I think most of you are starting and basically almost completing the homework. So basically for this case, I think you can do it is y over s and times s squared plus 2s plus 3 equal to 1, and ys equal to 1s squared plus 2s plus 3, right? And so for this case, you simply y of t, and you can take the inverse Laplace transform of this one. Okay, so then you need to work on what is this one, right? So you need to take the inverse Laplace transform of s squared plus 2s plus 3, right? So how to do that one? Here we can do this one here. Let me continue. So basically 1s squared plus 2s plus 3, we can utilize the skills we have earlier. Basically here, let me factorize this into, let me pick this as the hint to factorize the denominator in the product form. I start with observing the two terms, so that gives me the sense I need to come up with 2s plus 1, this term, and then because this 1 plus the other 2 should be equal to 3. So this gives me this sense. So in this way, this one can be written as s plus 1 squared plus 2 over 1, right? Okay, and now come to this point, then check out from our Laplace tables. From this table we have is s plus b squared over b, and that corresponding is sine bt, right? And in addition, because here we have this one, so we have to do this another kind of transform is s plus a squared plus b squared b, and that one corresponding is e minus at times sine bt. Okay, so now I simply take up these as the patterns to get a transform. So right now the effort is to get this term be in this template. Okay, so in this case, from here you can compare b equal to square 2. So I need to convert it s plus 1 squared plus b equal to square 2 squared. So I need to come up with square 2. Then here I divide by square 2, make those things equal. Be good? So that means here this is the Laplace transform of this one, basically here is y of t is the Laplace transform of this term is square over 2. Then we pick up that one is e. A is equal to 1, so minus t. And b equal to square 2t. You good? Okay. And the handouts give to you today is just doing the symbolic calculations of these numeric examples here. Okay, so if you can go over this one in terms of the symbols, basically the similar process like we did here, but a little bit more generic in terms of the symbols here, that is the handout I give to you. Okay, so that is the second, the solution process to this. And this is the solution process, and eventually what we obtained, if you have a handout, and given these systems, then we obtained is this solution y of t, and that basically is just like we saw here, similar to that one. This is the symbolic solutions of the y of t, given that one, basically represented by the symbols. Okay, and look at here, we have a little bit more the features. One is yt is a function of zeta. Zeta is the damping ratio, and here for this case in particular, we consider zeta is less than 1. And we also see the omega n. Omega n is the natural frequencies. And also we have one more defined variable called theta. Theta basically is in terms of the calculations, and we introduce theta as defined as the cosine of zeta. Okay, this is a very long equations, and let me give you a little bit more physical insight to that equations. While I erase the whiteboard, probably you can take a quick peek on the handout to see the solution process and get familiar with these things. Okay, so this solution is given by this one, and then let me do a little bit more tweeting about the result here. So basically yt equal to 1 minus, and let me repeat this one. So basically here, let me draw these things here. So this is the yt, and this is time, and this is the value of 1. Okay, this is a value of 1. And here, from here you can see this basically is equal to 1 minus zeta squared and exponent minus zeta omega nt, and multiply with sine something. Okay, later I'm going to fill this. Look at this form. And what is this form? This form basically, you can see this one is a scale. This one basically is one exponential decaying and multiplied with certain constant. So basically this term representing is exponential decaying. So let me put the graph to here. So that means you can see when t go to infinity, the whole terms will go to 0. Right? So that means yt is steady state. So that means the value, the steady state, that means steady state of yt equal to 1. Right? So that means whatever the response, eventually the value of yt will approaching to this level. And that is steady state response. Okay, so now I take care of the steady state response of the yt. And now we want to take care of the transient response. So basically, transient response will be determined by this term. This term, you can see, is a feature, is this. It oscillated in terms of sine or sinusoidal functions. And also the magnitude of this sine function is governed by this value. This value represents is the magnitude of the sine function. And here the magnitude is in exponential decay. So here you can see, I try to draw it. This sine function is something plus theta. So basically, when t equal to 0, it has a starting point. So the sine function was starting from here. Okay. So basically, the sine function and the exponential decay. So here is the profile of the minus theta omega nt and divided by 1 minus theta squared. Okay. So this profile is given by this, and this is a sine function. Theta. Okay, so eventually this one will be keeps oscillating, and then converge to the value of 1. So this is a feature of these dynamic systems. Okay, be good. Okay, continuously there's a features, and so given the features, from here you can see this is a peak and this is a peak. So from peak to peak, that is we call the period. So that is a period of oscillations, right? So the period of oscillation is equal to how much? Equal to 2 pi divided by the frequency of oscillation. What is the frequency of oscillation? This one. This term is frequencies of oscillations. Okay, so that is the first one. This is I think the few notes. So here is additional, and then furthermore, the decaying actually is divided by this constant. This is the constant to govern how fast the exponential decay. So for example. So for example, here we can see E minus T and E minus 2T. Which one decaying fast? This one. If you plot it, you can see this is T, and this is the E minus 2T, and this is the E minus T. Okay, so basically the coefficients of this one govern how fast it's decaying. So this is the term here. Okay. In controls, in particular in terms of dynamic analysis of the control systems, we have a way to incorporate this constant and the frequencies together by doing this. Look at the systems again. The systems the characteristic equations, by definitions, is equal to s squared plus 2 zeta omega ns plus omega n squared equal to 0. And this is by definitions. But in precisely, that one I can show you is this. Say, if we have, what is this one? What exactly is it? Okay, so let me show you more physical insight about these characteristic equations. So here again, this is our system. Let me rewrite our systems. Okay, and then here let me say take up whatever the type of the input signal. Let me call it RT. RT can be constant, can be anything you name it, and let me take a generic. Okay, so assuming we don't consider the influence of the initial conditions, so let me simply just take out the initial conditions equal to 0. So basically we don't consider that influence. So in this way we take the Laplace transform. Then what we get is y times s squared plus 2 zeta omega n s plus omega n squared equal to r of s. So again, Here in our definitions, the plus y equal to defined by y of s, the plus of the r of t, we define as the r of s. Okay, so that is our definition. So I introduce the symbols here. So with this one ready, and again, we can put into that kind of log form, and this is the y of s, and this is the output, and this is our input. This one is simply s squared plus 2 zeta omega n times s times omega n squared, right? So basically, what is the characteristic equations in reality? That one basically is setting the denominator of this equal to 0. Be good? Okay, so this one, this is called the transfer functions. So basically from here, let me write up here. So continuously, we can see y of s of y over r equal to this s squared plus 2 zeta omega n s and plus omega n squared. Okay, so this one is called the transfer functions. Transfer function representing is the ratio of output to input. So basically that is the output with respect to input in terms of the S domain. So these are transfer functions. The denominators equations, we set up denominator, that is these equations, and s squared plus 2 zeta and omega n squared. So these are denominators. We set the denominator equal to 0, and this is our characteristic equations. You good? Okay. So now the root, so that is to answer this question, what exactly the characteristic equation is. Basically that is meaning the polynomial equation in the denominators of the transfer function equal to 0. Okay. So the root of the characteristic equations s squared is equal to, basically the root of that one basically equal to, if we plug in, the s squared plus as plus b plus b s b plus c equal to 0, as then s equal to 2a minus b plus b squared minus 4ac, right? I simply take up these equations. So with this one, then the root of this equation will be equal to s, will be equal to, look at this carefully, and we plug in this equation, plug in here the a equal to 1, and b equal to zeta omega n2 and plus minus b squared minus 4ac, so that is 2 zeta omega n squared minus 4 minus a minus c, this one. And we do a little bit simplifications. Basically here the s will be equal to minus zeta omega n plus minus omega n times 1 minus zeta squared. Okay, so that is the root of the characteristic equations. And the root of the characteristic equations, and the root of the characteristic equations, that means we sometimes call the poles. By definition, the poles are the spatial terminologies in control. Basically, we call the poles. The poles are the roots of the characteristic equations, nothing spatial. Okay? So basically here we have 2 poles. For second order differential equations, we have 2 poles. For third order differential equation, we have 3 poles, and etc. Okay, and to this moment, any questions about the process? Good? Okay. Here I made a mistake. This should be complex numbers. Sorry. Okay, if you solve for that one, this should be the complex number if you look at this one carefully. Okay, so j equal to square root of -1. Okay. So basically, these are complex numbers. So in this way, this is the real part. And I don't need to write it. This is the real part, and this is the imaginary part, right? Good? Okay, and now we will be coming to the most important conclusions here. We back to your lecture notes. A few minutes ago, we will look at this diagram, this drawing here. In this drawing, I specified two important numbers. The numbers are, first one, how fast the decay will be, and I said that one is governed by this number, right? The second one is how quick, how frequent oscillation will be, and that is governed by this period. Actually, it's governed by the oscillation frequencies. So from here, you can see this one is actually, let me include the minus here. This part actually is the real part of the poles. This part is the imaginary part of the pole. Okay? Okay, so that means if you, let me make a quick conclusions. Once you are given any dynamic systems, you quickly solve for the transfer functions like this. Okay, from given this and to here, that shouldn't take too much time given your capability now. Okay, and once you have this one, this is the transfer function, that is the ratio between output and input. Then you simply go into the denominators. You find these. You set denominators equal to 0. You find the roots, and from there you can see the real part of the roots will govern how fast the decay will be. The second portions, the imaginary part, will tell you how frequent this oscillation will be. If, for example, in one scenario, if your solution of the roots have no imaginary part, then you should expect the solution have no oscillations at all. Be good? If you, on the other scenario, if you solve for the root and you find, oh, the real part is positive, what means positive? Positive, that means exponentially growing. Be good? Okay, think about this one. And so right now I successfully, we're starting from the review, the solution process and into the time domain, and gradually kind of guide everyone to our content, the transfer functions and the poles, and then from there we build up the relations between the numbers and to the real things. Okay, so build up a mental pictures of the response. I think that is the most critical step for everyone to be good. I mean, to be good learners in controls. Okay. Then with those things, then we can do this one here.